Hello again. This is Math 2233 coming to you from the College of DuPage. And this lecture is the conclusion of the lecture entitled Maximum and Minimum Values in a Multivariable Setting, wherein we discuss absolute max and min. As always, please be an active learner as you watch this video. So we're going to be talking about absolute maximums and minimums. So recall from Calc 1, for a function of one variable, the extreme value theorem said that if f is continuous on a closed interval from a to b, including the endpoints, then f has an absolute minimum and an absolute maximum value. According to the closed interval method that we discussed in Calc 1, we found that we evaluate f within the interval using the critical number approach, but also at the endpoints of a and b. Well, there is a similar situation for functions of two variables. Just as a closed interval contains its endpoints, a closed set in R2 is one that contains all of its boundary points. A boundary point of D is a point AB, such that every disk with center AB contains points in D and also points not in D. So for example, the disk D equal the set of xy such that x squared plus y squared is less than or equal to 1 is a closed circle. So anything on the boundary of the circle, if you draw a circle around that, contains points inside and points outside. So this consists of all points on or inside the circle, x squared plus y squared equals 1. And the x squared plus y squared equals 1. In fact, the closed set, the entire closed disk is a closed set because it contains all of its boundary points. But even if one point on the boundary curve were omitted, the set would not be closed and the theorem would not be true. And here's one where there are gaps on the boundary. And here's another one where there are gaps on the boundary. So we define a bounded set in R2 is one that is contained within some disk. That means you can put a disk around it. In other words, it is finite in extent. Then, in terms of closed and bounded sets, we can state the following counterpoint of the extreme value theorem in two dimensions. And there are multiple dimensions higher than 2 where this is also true. So the extreme value theorem for functions of two variables. If f is continuous on a closed bounded set D in R2, then f attains an absolute maximum value, f evaluated at x1, y1, and an absolute minimum value, f at x2, y2, for some points x1, y1, and x2, y2 that are in D. Now to find the extreme values guaranteed by this theorem right here, we note that by earlier theorems, if f is an extreme value at x1, y1, then this is either a critical point or a boundary point. Thus we have the following extension. To find the absolute maximum and minimum values of a continuous function on a closed bounded set D, find the values of f at the critical points of f in D. And then find the extreme values of f on the boundary of D, and take the largest and smallest of these, and those are the absolute maximum and absolute minimums. So there's a problem for us to practice then. Find the absolute maximum and minimum values of the function z equals f of xy equal x squared minus 2xy plus 2y on the rectangle D. That is a set of xy such that x is between 0 and 3 inclusive and y is between 0 and 2 inclusive. And you can see that is a closed boundary. And so we're going to be looking at this twice. We're going to be looking inside on the open set, and then we have to look at the boundary. And there are different parts of the boundary. There is L1, L2, L3, and L4. You know what to do. Let's see how you did. Okay. So since f is a polynomial, it is both continuous on the bounded and closed set. And that tells us that by the theorem, there is an absolute maximum and absolute minimum. So what we're going to do is we're going to seek the critical values. So we were going to take the partial with respect to x and the partial with respect to y of this function. The partial with respect to x is this expression. The partial with respect to y is this expression. We solve these simultaneously, but that gives us only one critical point, that is 1, 1. And the value of f there is, if we put 1, 1 into this equation, we will get f of 1, 1 is 1. Now in step 2, we have to look at the values of f on the boundary of D. And there are 4 line segments, as we said before. So we have L1, L2, L3, and L4. On L1, we have y is equal to 0, so we have a function of a single variable. Well, this, the max or min of this happens either at the boundary or inside, and that's when 2x is equal to 0. What we're going to do then is we'll realize this is an increasing function of x, so its minimum is when we're at 0, the lowest value within that interval. And so the minimum value is f of 0, 0 is 0, and its maximum value is f of 3, 0, which is 9. On L2, we have x equal 3, and so we have again a function of a single variable. Y is the only variable, and we can use first term calculus techniques to realize that the maximum value there is f3, 0 is equal to 9, and the minimum value is f3, 2 is equal to 1. On L3, we have y is 2, and so f of x2 is this, and so we have this expression. So we're finding the max and min there. Using the methods, we can take the first derivative, or perhaps we could even realize that that is by completing the square. So the minimum value of this function is f22 is equal to 0, and f02 is 4. And finally on L4, we have x is equal to 0, and we have this. And again, we're on a closed set, so the maximum value here is 4, and the minimum value is 0. So that tells us about the boundaries. So now we combine these results, and we can conclude that the absolute maximum value of f on D is f3, 0 is 9, and the absolute minimum is f00, which is the same as f22, is equal to 0. So we have found the minimum, and we have found the maximum. And here's a picture of what we have found on that surface. And so on that closed boundary, those are the minimum and the maximum values of the function occur at these values. Now, we're going to return and do one other thing within this lecture, and that is we're going to go back and talk about the proof of this second derivative test. You remember this happened a couple lectures ago, but we had this expression. This is the second derivative test, and we're going to prove part A. The other proofs are going to be similar, and you should be able to complete those based on what we do here. But what we're going to do is we're going to take this expression for D, and let's in fact talk about it, what we're going to prove. So suppose the second partials are continuous on a disk with center AB, and suppose that the partial of f with respect to x and y are 0 at a point AB. That means it's a critical point. And D is this expression. It's going to be the second partial of with respect to x times the second partial with respect to y minus the cross partial whole squared. And we're to prove if D is bigger than 0 and fxxab is bigger than 0, then this is a local minimum. Okay, so let's compute the second order partial derivatives in this direction, and this is a directional derivative. Now the first derivative is this, because we're taking in the direction of hk, that means this is a unit vector, and that's just the dot product as we've learned earlier. But now we're going to take the derivative of this yet again in that direction. So you see, when we do that, it's going to be the directional derivative of the directional derivative, again in the direction of u. So it's going to be partial with respect to x of this dotted with h and dotted with k. There's a k here that got erased. And so I will combine like terms, factoring out the h's and k's. And that is what I get after I do the calculation. And so I'm going to get this, and notice that the partial with respect to x and y and the partial with respect to y and x are the same. And the reason those are the same is because we have Clairaut's theorem. That's a theorem that we proved if the partials are continuous. Those expressions are the same. But now what we're going to do is we're going to complete the square here. And so when we complete the square, we're going to factor out the f xx from the term and complete the square for that, and then we're going to complete the square on the other one, and here we're factoring out k squared over fxx, and we get this expression. Make sure you follow this calculation. Now we're given that fxx is greater than 0, and this is greater than 0. And also we're given that that this expression is also greater than 0. But they're continuous functions, so that means there's a disk where they're also greater than 0. So that means that the second partial is greater than 0 whenever we're in that disk. That means if the C is a curve obtained by intersecting the graph of f with a vertical plane through AB and f of AB in the direction of u, then it's concave upward on this interval, and that's true in any direction that we go. So if we restrict xy to lie in that bounded set, then the graph is above its horizontal tangent line. That means it is a minimum at AB. In closing, now, more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of each other. May God bless you all.